Welcome to our presentation on blazing fast container deployments using image caching and block storage. My name is Juana Nakfour. I'm a principal software architect at NVIDIA, mainly working on enabling AI workflows on Kubernetes. And my co-presenter, Manu, here.
Yeah, hi, guys. My name is Manu Bhadoria. I'm with NVIDIA leadership at working with GeForce Now, a product. This is my first time at KubeCon and first time presenting, so be kind, please.
Be nice.
Be nice to me.
So, of course, you're all thinking we threw more GPUs on the problem because we both work for NVIDIA, but not this problem. Maybe for our next presentation, because I think it's a good idea also to use GPUs to do this, solve this problem. All right, so we'll walk you through our experience with why pods are really slow to start up. And I think this question, everybody here that's deploying on production will ask that question, especially if you're scaling. And you have traffic going through your cluster, you're wondering when your pods are going to be ready. And I think this is also specific to AI workflows, because not only when your pod startups, not only are you waiting for a pod to be ready, but you're also downloading a model maybe from cache or from somewhere else, which takes a long time. So the problem is very specific to AI. The solution, we're going to walk you through what we did with regards to how we enabled Containerd to be faster and how we used remote block storage to solve that problem. And the last part, which is Manu's part, the most interesting part, is how we actually took this to production in one of our clusters, and then as a case study, and did it really work, and what are the numbers? All right, so we're going to dive straight into technical aspect of it. So when you deploy a pod, at some point, that pod's going to be scheduled on a node, and kubelet's going to get the spec for that node. And the first thing that it does is that it connects with Containerd, which is a process running on your Linux host on the container runtime interface, and it gives it information on the pod or the container that it's trying to load. So Containerd will look at the image first and try to see if it has seen it before, unpacked it before, or it hasn't, and it connects with the registry to get the manifest. The manifest is a file, as you all know probably, that it has information on every single layer that is part of that container image. So Containerd, again, will look into its container store to see, have I unpacked it before? Or do I know what it is, or do I not know what it is? And then Snapshotter comes into this picture. I have Snapshotter on its own, but it's actually part of Containerd. It's pluggable. You can plug in your own Snapshotter. And there's this dance going on between Containerd and Snapshotter through the Snapshotter interface on prepping this file system and unpacking these images into the file system. So if Containerd has not seen or has not unpacked this layer before, it will call the function called prepare on Snapshotter. And Snapshotter will look also in its own. That's another thing that you'll see later on that causes issues. It will look in its own database and see if it has unpacked it before or not. If it hasn't, it will create one and give it back to Containerd. Containerd will unpack these layers into this file system that's prepared, and then it will call a function called commit on Snapshotter, telling Snapshotter that this file system is ready. You can build the tree on top of it so that in the end, after we do this for every single layer, we have the file system ready to run the container, and that's what happens at the end. So we looked at all the different phases that we have here, and we measured the latency. And I think everybody here who's probably familiar with Containerd and its process knows that the problem is here. It's the unpacking part of these blobs or these layers. It took around 80% of the end-to-end latency. So we zoomed in on this part, and we tried to see how can we get around elevating this latency. And there are other solutions out there where you can custom create the images and then unpack them to unpack them faster, but we didn't want to go away from the norm of doing Docker builds, and we wanted a solution that just zooms in on this high-end latency. All right, so if we look at this at scale, we'll know that I call it node isolation. If you're scaling on hundreds and thousands of nodes, this problem is on every single node. There's no coordination between the different nodes in the same cluster, or maybe sharing some of the unpacked layers, or maybe sharing some of the images, or any coordination between Containerd across all these nodes. They're all working in isolation. So the problem is really magnified. The first thing that we thought is, well, if 80% of our end-to-end latency is unpacking these layers, then why can't we just unpack them in a remote drive that's backed up by a remote block storage and just give it to Snapshotter and make it read it from there? Well, the default Snapshotters cannot handle 2 drives, so we had to write our own. It's basically, we wrote it over overlay.fs, which is one of the default containerd snapshotters. And we configured containerd to use our custom snapshotter, which is a standalone process on your node, on your host node. And what it does is, what we did is we unpacked the most popular base images that we have for our containers. And if we didn't have a popular one, we actually made all our engineers use a very good solid one. And we unpacked it previously in the same method that custom snapshotter will unpack normally on these remote drives. And we plugged it into this custom snapshotter. So now it has two drives. The local drive is everything that's being downloaded currently while runtime. And then the remote drive is everything that has been pre-unpacked and pre-stored there. So now containerd, if it gets a layer that it hasn't seen, it will call prepare for custom snapshotter. And custom snapshotter, if it finds it in its remote drive, will come back and say, I already have this. No need to unpack this layer. If we look at this at scale again, we'll see now there is some form of coordination between the nodes through that remote drive. So now every custom snapshotter on every node is going to look through to that remote drive to see what's being unpacked beforehand, before it actually tells containerd to unpack it. So in our initial investigation, before we took this to production, we did a little experiment on a single machine to try to see what impact or what the solution is, numbers and impact it has. We had 3 use cases. MicroK, worst case, we called it because it had nothing on it. MicroK with the base container, because we downloaded the base container beforehand. And then MicroK with our custom snapshotter. And a base that's already pre-unpacked. And we did 2 containers, and we measured the time for the containers to be ready. We did Nginx, which is really tiny, 0.05 gigabytes with a base of 0.03. And we did really big container, which is one of our NIM containers called BioNemo, with a base of Triton Server. Triton Server is our inference stack. It was a year ago 6 gigabytes, but it's a lot smaller now. And if you'll see the bottom 2 charts, on the right side, you'll see there's a lot more impact when the container is actually really big. That's the difference between, that's the difference between the blue, which is the worst case, nothing's there, and the yellow, which has microK. And the red is the difference between the red and the yellow is when you actually normally have the base layer there through microK, and when you have custom snapshotter sitting there as a remote process, using unpacked layers in a remote drive. So a kind of a summary, for large containers, we saw around 0.7x latency improvements, and the difference between the red and the yellow here, between the best use case and our custom snapshotter solution, was around 0.3x latency. All right, so next is the interesting stuff of how we actually deployed that on our clusters.
All right, hi guys. So I'm going to talk about the case study at NVIDIA in production, essentially, and that brings me to the topic of GeForce Now. So before I get into the details, how we did that, and the results, and some of the challenges and limitations, I would like to kind of touch upon some of the key terms. So I'm going to keep saying these names, so it's better to get familiar with them now. So first thing first, GeForce Now, it's our cloud-based game streaming application. It's subscription-based, so basically we have almost 1.2 million sessions, streaming sessions every day. We got 60 plus data centers globally, NVIDIA owned, and then basically these are zones, and we have 60 plus GPU deployed in cloud, 60 plus thousand GPUs deployed in cloud. And the main thing to call out here is the GeForce Now is kind of built on a high-performant, low-latency GPU cloud-based infrastructure, which is where you have some capacity to run some AI workload as well. And that's why I wanted to mention the GeForce Now. This is all being done on the GeForce Now platform. So NVCF is another aspect. The second key term is essentially just an abstraction layer and a set of APIs that is given to by NVIDIA. We provide these APIs, set of APIs for anybody to deploy their workload, define their workload, deploy to it, and it can deploy to any backend. So one of the backend is essentially the GeForce Now, and this is how they are interconnected. And the base container, Juana kind of already touched base upon it, but these are our building blocks of building your own container. For example, she gave about the BioNemo, one of the names, is built upon NVIDIA Triton server. So those building blocks are the one we are focusing on to kind of cache ahead of time, and that's the whole caching mechanism in place for. Now, how we do it is twofold. First, Juana already kind of briefed up on it, but it's we kind of prep these images, base images, we unpack them ahead of time, and we distribute in the GFN zone. So that's step one. Step two, you just leverage NVCF, or you can just leverage, you just define your workload and you deploy it into cloud, and GFN is one of the accessible cloud. So that's how we do it. So let's talk about, this is a little busy slide, so I'm gonna have to direct your attention to some of the spots here. But this is the step one of how prepare and distribution of these unpackaged base containers in GFN. So if you look at the top left corner, it's an automated pipeline. It's something that we run ad hoc and runs periodically. But essentially, all it does is kind of read this inventory of base containers, list of containers, downloads from NVIDIA container registry, unpacks them into a virtual block device, and that block device is ready for distribution. And we kind of push that to our NVIDIA central storage. But the main thing to call out in this automated pipeline, we leverage custom snapshotter in this pipeline itself. Basically, we use it in a pre-fill mode. It's kind of prepared the file system ahead of time. It unpacks it and prepares it, and those unpacked layers are now kind of stored as a file system inside a virtual block device. And that virtual block device is like a file. It gets distributed to GFN zone, and on the top right, you can see just an interaction between the services we host in AWS. But this is a service which is globally just allowing communicating with all the GFN zone and kind of just distributing, sending the signal that, hey, this new block device is available, why don't you just download? So on the bottom, you'll see our n numbers of GFN zones. So all these GFN zones have in-zone storage as well. And that is where these block devices gets cached by this delivery mechanism that we have in place. And you'll also see in the GFN zone on the bottom, there are worker nodes. And these are the GPU nodes. I'm going to speak to it in the next slide. So at this point, we have placed all these base container images inside the GFN zone on the storage itself. So they're in-zone cached at this point. So now the second step of how is basically we do a function creation and deployment. I forgot to mention that, but function creation means it's just you define your AI workload, what it looks like, what instance type you need, what model resources containers that you might need. That's the definition. And then you register that with the NVCF, and then you click deploy or schedule it. Basically, that workload gets deployed to the backend, and in this case would be GFN. Again, GFN is primarily for gaming. So NVCF is able to schedule the AI workload of yours during wherever there is a spare capacity. Since gaming is like a sinusoidal, like people go to work and they don't game 9 to 5 mostly, so there is spare capacity. What do we do? During those cases, we would schedule these AI workloads. So on the rightmost side, you can see the GFN zone. All these worker nodes are ephemeral GPU nodes. These are all essentially VMIs, VMs, and I'll talk about that a little bit. I'll zoom into the worker nodes in the next slide, but essentially these are just VM spinning up, connected to the storage, and essentially these GPU nodes have connection to the storage. And remember, those storage has these cached base images already. Okay. So let's zoom in onto one of the GFN zone. And as I mentioned, there is a storage on the left side, and then basically the worker node is the ephemeral node with the GPU attached to it. And I've removed a lot of complexity and just kind of abstracted away everything. So just wanted to highlight the key component. Within the worker node, we have these VMIs running. The virtual machine instances are running in Kubernetes, and within that we got micro K8s set up. So and within we configure the micro K8s to use this custom snapshotter from Juana's team. And we configure it in a way that it also points to the remote drive. And the remote drive is nothing but just a network connection to the storage in the zone itself. So at this point, the custom snapshotter sees a remote drive and also a local drive is available. So when your workload is deployed, the container D is now talking to custom snapshotter, which has access to this cached images and also local device. So it's just going to see that if some of those base containers, if it's in your list of workload containers, are already cached or not. If it is, nothing goes out to the internet, nothing downloads from the registry, it's already unpacked. It's a no-op, it just custom snapshot comes back to container D and say that, hey, everything is there. If not, cache miss, it goes to the registry, it does all of that, download and extraction, and that's where we see the time. So that's pretty much it within the ephemeral node. Now let me walk you through some of the data points here. And I kind of zoned in on some data points from one of the specific workloads that we deploy every single day. And this is to test our end-to-end functionality every single day. Devs and QA have really leveraged this test. So I want to kind of, and this is running in production every day. So we have, of course, feature flags to use the custom snapshotter or not to use it. So when we use the custom snapshotter, which has access to this remote drive and the cache layers, we definitely see the benefit in terms of time. So you can see that it took us just 5 seconds to deploy that. I remember this workload is defined by us. And we are heavily using our recommended base containers. So of course, we get the benefit of it because they are already cached. And in case of cache miss scenario, when we disable the feature just to show the value of it, we see that it all does an extraction and whatnot. So it took almost 3 times more, I'm losing my chain of thought, but yeah, it takes more time to actually deploy your workload itself. Essentially, we get a lot of benefit if it's cached. And it's just not the time. When you deploy a workload, you're also doing this on a GPU node. So you don't want to consume GPU node just for downloading, prepping, and all that. You want to use it for inferencing, of course, right? So that's where it brings a lot of value too, cost as well. And again, this varies. This varies just because base containers are recommended containers that we would like you to use. And not all the containers are built equally. So this results varies a lot based on how much they are using the base containers or how much they are not. And hence, we see a lot of different results. But I wanted to kind of focus on what we use as a best practice, and this is what the results we get. And finally, let me touch base upon some of the limitations and challenges that we have faced. It's not all perfect, but we are working towards that perfect solution. We can always be working towards a perfect solution, but one of the main challenges is the behavior in the long-standing K8s cluster. Remember, this is all happening within the ephemeral GPU node and a micro Kubernetes setup inside it. So your workloads inferencing is done, that ephemeral node is down, and then a new ephemeral node comes up with a new micro Kubernetes cluster and basically container D and custom snapshot. So this means if you need to do any kind of if you need to replicate that same setup in a long-standing Kubernetes update, so a cluster, then all the nodes have to be drained just in case you actually have a new container D release or a new custom snapshot or fix or something. So it has to be all drained, and that is so unpredictable, and there's a big operational overhead. So this kind of works for us in that environment where we are spinning up these ephemeral nodes with the micro Kubernetes cluster. But in the long-standing K8 cluster, yes, there is an operational overhead in that scenario. And another thing is the unpacking of the container images. So these are the ones which are recommended ones, and there is a list of it. So we always have to sort of play catch up and always have to update our NVIDIA Triton server would be updated. So we want to use it and we want to move the customer to the latest and the greatest. So there's always that balance of us updating our inventory and kind of preceding this content. So there's always that. And of course, this is open to another limitation, or it's sort of a limitation, but it's open to our mostly for the public images that are present in the NVIDIA container registry. Another limitation is, since we now introduced our new service, the standalone custom snapshotter, of course, this is like a whole engineering support that is kind of falls with it. So, so that's another it's a challenge. It's engineering overhead, you can call it, but we have to support it. We have to monitor it. We have to do a lot of updates and continuous life cycle of software development. And yeah, these are our challenges. And thank you so much for having us here today. Appreciate it. Thank you.
Thank you.
Questions? If anyone has any question.
Yeah, happy to answer.
Hi. So I saw the image building and like deployment. So
Yeah.
For the remote storage, what are you using as a backend? And like, let's say if there are too many images, does it have an internal LRU to, let's say, kick off things which are now not being used?
Oh, yes, that's a good question though. From the cache eviction perspective, right? Yeah, so there are basically, we kind of, so these container images that we download, so we kind of have a very simple eviction logic here. We give a quota of like 10 terabytes and pretty much that's it. And then it's basically first come, first out. So basically we are just always updating it and we can always revert to it. But it's not like, it seamlessly gets evicted just because new workloads are coming and are connecting to the storage.
Okay.
So it's just basically, it gets updated to the latest one. So there are internal configurations that we up and say point to that, hey, use this new virtual block device. So it's just that. And the ones that are not being used gets evicted after 30 days or some basic eviction policy.
Got it. And what is this backend you're using for the remote block storage that is connected in each zone?
Yeah, so these are our GFN storage. So basically these are SMB-based file systems. So that's why I call it like a virtual block devices. We create them as a file. So those are available as a virtual block device to the GPU nodes. Yeah.
Is there any other question?
So just to clarify, you're creating a file system image and then you're putting that inside the container and then mounting that once the container's up and running, or?
So these are the virtual block device, like these are files. Basically, you can mount them in a read-only fashion and kind of open them up. It's
They're mounted to custom snapshot.
Yeah.
Custom snapshot prepares the file system. And when it does preparing the file system, it copies some of these from the remote drive to a local drive. So it presents it to the container.
And so this would get around the time that it would take to create hundreds or millions of files or whatever it is that you're creating when you lay out this file system. Is that where the time was taken up?
No, the biggest latency was actually unpacking the layers.
Right.
Yeah.
Okay.
It wasn't prepping the file system.
Yeah, thanks.
Thank you. Let's say I would like to introduce your custom snapshot in my environment. How will I do that? How can I use your custom snapshot to unpack the layers and get?
It's not open source. You have to write your own.
Sorry.
Hopefully we'll get there one day, but we still need to work on a lot of the things that we just discussed with long-standing clusters.
Yeah.
Yeah.
You can't use it right now. That's it.
Question here. Did you ever benchmark using a remote network file system instead of remote block storage?
I don't think we did.
So, sorry, what was the question again?
Did you ever benchmark using a remote file system instead of remote block storage?
The block storage technology in GFN is pretty new. It's coming up. Basically, we don't have that. So we use what we have. And that's...
Yeah. The answer is no.
No, we did not.
Okay.
A remote file system would probably be a lot slower.
Any other question? Don't worry, exercise.
Maybe they should walk to you.
No.
There's a speaker, yeah. There's more here.
Thank you. I wanted to ask about like caching those images. I think you said like you constantly update the cache.
Yeah.
And I was going to ask like how often and how do you ensure like when you're deploying to like you said 60 plus K right data centers, how do you ensure like all those deployments using the last image? Like how is there some sort of scheduling?
Yeah, so that's a good question. So basically, we run these pipelines ad hoc when we know that we have updated the inventory, and they run periodically, almost every day. So it just kind of, if there is no update, it's a no-op. If there is an update to the inventory itself, yes, we distribute them to the GFN zones, and these are like 60 plus zones. And then we have the scheduler inside the GFN zone, which actually spins up these worker nodes. So we update the configuration of the scheduler to be able to pass information to worker node that use these new block devices. So it's basically we update the configuration. It's always using the latest one, and we can always change that to the previous one because we have some retaining of the previous ones. I think we run out of time. So thank you again, guys. Appreciate it.
Thank you, everyone.